Hello, and welcome to Space for Sleep. Mars is close enough to feel almost familiar and distant enough to remain profoundly alien. It turns in the same sunlight that warms Earth. It has a day only slightly longer than ours. Its axis is tilted in a way that gives it seasons. Its surface preserves riverbeds, lake deposits, deltas, glaciers, volcanoes, dust storms, polar caps, and the scars of ancient impacts. Of all the planets beyond Earth, Mars is the one that most often invites comparison, not because it is truly Earth-like now, but because it once came close enough to Earth-like conditions to make the comparison scientifically meaningful. That is what gives Mars its particular power. It is not simply the red planet of old mythology, and it is not the inhabited canal world imagined by 19th century observers. It is a real place with a real history, a small rocky planet that began with enough heat, water, atmosphere, and geological energy to become one of the most important worlds in the search for life, and then changed. Over billions of years, it lost most of its atmosphere, most of its surface water, and much of the environmental protection that once made liquid water possible. The planet we see today is cold, dry, thin-aired, irradiated, dusty, and quiet. But its rocks remember a different Mars. That memory is why we keep going back. Every orbiter, lander, rover, helicopter, seismometer, drill, spectrometer, and sample tube sent to Mars is part of one large question with many layers. What was Mars like when the solar system was young? How much water did it have? How long did lakes and rivers persist? Did the planet ever develop habitable environments stable enough for biology? If life began there, did it leave traces in minerals, carbon chemistry, isotopes, textures, or buried sediments? And if Mars was once habitable but is mostly not habitable today, what does that tell us about the fragility of habitable worlds? One way to understand Mars is to treat it as a planetary experiment that began almost like Earth and then diverged. Earth and Mars formed from broadly similar rocky material in the inner solar system. Both began hot. Both were struck repeatedly by leftover planetesimals. Both differentiated into core, mantle, and crust. Both had volcanic activity. Both likely had early atmospheres much thicker than what Mars carries now. Both had water. And for a limited period in the first billion years of solar system history, both worlds may have offered environments where liquid water and chemical energy existed at the surface. Then the paths separated. Earth was large enough to hold heat longer, sustain long-term geological cycling, maintain a magnetic field, and preserve a dense atmosphere and global ocean. Mars, being smaller, cooled faster. Its magnetic dynamo shut down early. Its atmosphere became vulnerable to the solar wind. Its water was lost to space, trapped as ice, buried underground, or locked into minerals. Its surface crossed a threshold from active and wet to cold and oxidized. The result is not simply a smaller Earth, but a record of what can happen when a rocky planet loses the conditions that keep habitability stable. This makes Mars scientifically valuable in a way that goes beyond exploration romance. Venus shows what happens when a rocky world becomes too hot and develops a runaway greenhouse climate. Mars shows what happens when a rocky world becomes too small, too cold, and too exposed to space. Earth lies between them. The three inner worlds form a kind of planetary comparison in climate, atmosphere, geology, and habitability. Understanding Mars is therefore also a way of understanding why Earth remained habitable and how fragile that habitability may be over geological time. The temptation is to think of Mars only as a destination. But before it is a destination, it is a lesson. It teaches that water alone is not enough. A planet may have water and still lose surface habitability. It teaches that an atmosphere is not just air, but protection, pressure, insulation, chemistry, and climate stability. It teaches that a magnetic field may matter not because it is a magic shield, but because it changes how the solar wind interacts with the upper atmosphere over billions of years. And it teaches that habitability can be temporary, real, meaningful, and scientifically important, yet not permanent. Mars has also repeatedly disappointed the simple stories humans try to place on it, and then replaced those stories with something more interesting. It was not the world of canals. It was not a living desert with visible vegetation. It was not a simple dead moon-like body after Mariner 4, because later orbiters revealed a far more complex planet. It has not yet given us life, but it has given us ancient habitability. It has not given us easy settlement, but it has given us a realistic frontier where engineering, biology, geology, and ethics all meet. The planet keeps refusing the easy answer. This is why Mars appears so often in astrobiology. It is not because scientists expect to find animals, plants, or a hidden civilization. It is because Mars once had environments where microbial life, if it could begin, might plausibly have survived. The question is narrower than old science fiction and more profound. Did chemistry cross the threshold into biology twice in one solar system? If it did, life may be common in the universe. If it did not, even when Earth and Mars both offered early habitable environments, then the origin of life may be more difficult than our single successful example makes it appear. So we will move through Mars carefully. Its orbit, its size, its surface, its weather, its lost atmosphere, its water, its moons, its history of exploration, its open question of life, and the difficult possibility of sending people there. Mars is not a gentle world, but it is a readable world, and we are learning to read it line by line. There is another reason Mars holds attention so well. It sits at the boundary between the known and the unresolved. We know its diameter, its gravity, its atmosphere, its seasons, its mineralogy, and the chemistry of many rocks on its surface. We know where rivers once flowed and where lake sediments were laid down. We know the names of specific stones examined by rovers, the depth of craters, the shape of ancient deltas, and the seasonal rhythm of carbon dioxide frost. But the largest questions remain open. We do not know whether Mars ever had life. We do not know exactly how warm its earliest climate was, or for how long. We do not know how much liquid water remains underground today. We do not yet know what the most promising samples will reveal when, or if, they are returned to Earth. That mixture, precise knowledge and deep uncertainty, is what makes Mars more than a catalog of facts. It is a world where the evidence is strong enough to guide us, but incomplete enough to keep the story alive. The aim is to stay with that real Mars. Not a postcard, not a myth, and not a sales pitch for colonization, but a planet whose actual science is deeper than the fantasy. Mars rewards patience more than certainty. A cold desert can still be calming when its history is clear, when the scale is held carefully, and when the unanswered questions are treated with respect rather than noise. Mars is quiet enough for sleep and complicated enough to reward attention. The familiar facts are only the entrance. The real story is the tension beneath them. Water without a final answer, organic chemistry without proof of biology, missions that have transformed the planet without exhausting it, and a future destination that remains harder than the dream makes it sound. That is why this world can carry a long, quiet episode without becoming small. The more carefully Mars is described, the less ordinary it becomes. It remains close, red, silent, and unresolved. And that is enough to begin. Slowly, carefully, and without pretending the answers are simpler than they are. That is the Mars worth listening to. And it is where we begin now, with the real planet in view. Mars is the fourth planet from the Sun, orbiting at an average distance of roughly 228 million kilometers, about 1.5 times farther from the Sun than Earth. But this average distance can be misleading. because Mars has one of the most elliptical orbits of any planet in the solar system. At its closest approach to the Sun, called perihelion, Mars comes to within about 207 million kilometers. At its farthest point, called aphelion, it swings out to about 249 million kilometers. This difference of 42 million kilometers between closest and farthest means that Mars receives significantly more solar energy at perihelion than at aphelion, roughly 45% more, and this variation plays a significant role in driving the planet's seasonal cycle in ways we'll come to later. The distance between Earth and Mars changes considerably over time. When Earth and Mars are on the same side of the Sun at roughly the same point in their orbits, an event called opposition, Mars can come as close as about 54 million kilometers to Earth, which in cosmic terms is a neighborly distance, reachable by spacecraft in roughly 6 to 8 months with current propulsion. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance stretches to over 400 million kilometers. This variation in distance is one of the primary constraints that shapes the planning of missions to Mars. There are specific windows, roughly every 26 months, when Earth and Mars are positioned such that a spacecraft launched from Earth can reach Mars with the minimum required fuel and travel time. These launch windows are narrow and unforgiving. Miss one, and the next won't arrive for over 2 years. The journey from Earth to Mars, even under favorable orbital conditions, takes roughly 6 to 9 months, depending on the trajectory chosen. During that journey, a spacecraft, or eventually, a crew, would travel through the inner solar system in a long, curving arc called a Hohmann transfer orbit, coasting through interplanetary space with no direct connection to anything, entirely dependent on the supplies, power, and systems carried along for the journey. No resupply, no rescue. The sheer isolation of that journey, hundreds of millions of kilometers from Earth with communication delays of up to 20 minutes each way, is one of the most serious challenges facing human missions to Mars, and one that is easy to underestimate when looking at Mars as a point of light in the night sky. Reaching Mars is only half the difficulty. Landing there is its own engineering trap, often called the 7 minutes of terror. Mars has enough atmosphere to create violent heating and aerodynamic forces during entry, but not enough atmosphere to slow a heavy spacecraft gently with parachutes alone. A lander arrives at interplanetary speed, hits the thin upper atmosphere, survives the heat shield phase, deploys a parachute in supersonic flow, sheds velocity, then must use rockets, airbags, a sky crane, or some other final descent system to reach the ground. The atmosphere is too thick to ignore and too thin to trust. That awkward middle condition is one reason Mars has destroyed so many spacecraft. Mars completes one orbit around the Sun in about 687 Earth days, just under 2 Earth years. A Martian year, in other words, is nearly twice as long as ours. And because both planets are orbiting the Sun at different speeds, Earth moving faster, Mars more slowly on its wider orbit, the repeating pattern of distances and positions between them takes on a complex, slowly cycling character. The closest oppositions of the last century occurred in 2003, when Mars came within approximately 55 million kilometers of Earth, a distance not seen in nearly 60,000 years. The next extremely close approach won't happen for centuries. The geological time periods of Mars help organize this story. The Noachian period, beginning more than 4 billion years ago and lasting until roughly 3.7 billion years ago, was the era of the oldest heavily cratered highlands. It was also the period when valley networks, clay minerals, and ancient lake environments were most common. If Mars ever had its best chance for surface habitability, the Noachian was probably that time. The planet still retained more internal heat. Its atmosphere was likely thicker. Impacts were more frequent. Volcanism was intense. Water interacted with rock for long periods, creating clay minerals that preserve evidence of relatively neutral to alkaline water, not necessarily gentle by Earth standards, but chemically more favorable for life than later acidic environments. The Hesperian period followed, roughly from 3.7 to 3 billion years ago. Mars was changing. Large volcanic provinces continued to shape the surface. Outflow channels recorded catastrophic floods, perhaps released from underground reservoirs by volcanic heating or impacts. Sulfate minerals became more common, suggesting water that was often more acidic in environments that were becoming harsher. Mars may still have had lakes and flowing water at times, but the stable warm surface conditions of the earliest period, if they existed at all, were fading. The Amazonian period, from roughly 3 billion years ago to the present, is the long, cold chapter. It includes most of the Mars we see today: dry, dusty, thin-aired, dominated by wind, ice, impacts, and slow surface alteration. But even the Amazonian is not completely static. Young lava flows, recent gullies, recurring slope features whose interpretation remains debated, fresh impact craters exposing ice, shifting dunes, and active dust cycles all show that Mars is not geologically frozen in the simplest sense. It is quiet compared with Earth, but quiet is not the same as dead. These time divisions matter because life, if it ever existed on Mars, would not have had equal chances everywhere and everyone. The best preserved biosignatures might not be in the youngest surface material. They might be locked in ancient mudstones, clays, carbonates, silica deposits, or buried sediments that formed when liquid water was present and then remained protected from radiation and oxidation. This is why landing sites such as Gale Crater and Jezero Crater were selected with so much care. A rover is not simply sent to a picturesque place. It is sent to a geological archive, where the layers tell a story and the instrument suite is designed to read that story in chemistry, texture, mineralogy, and context. Let's talk about Mars itself, the planet's physical character, its size, its gravity, its day. Mars is considerably smaller than Earth. Its diameter is about 6,779 kilometers, roughly half of Earth's 12,700 kilometers. It has about 15% of Earth's volume and about 10% of Earth's mass. Its surface gravity is approximately 38% of Earth's, so a person who weighs 80 kilograms on Earth would weigh roughly 30 kilograms on Mars, a reduction significant enough to feel profoundly different in every physical action, from walking to lifting to simply breathing the effort of movement. This lower gravity has consequences that go beyond personal comfort. It means Mars couldn't hold on to its atmosphere as tightly as Earth holds on to ours. Over billions of years, a combination of lower gravity, the absence of a strong global magnetic field, and the persistent erosion of the upper atmosphere by the solar wind has stripped Mars of most of the thick atmosphere it once possessed, leaving behind only a thin remnant, about 1% the density of Earth's atmosphere at sea level, that provides little protection from radiation, little insulation against cold, and insufficient pressure for liquid water to exist on the surface. A Martian day, one full rotation of the planet, is 24 hours and 37 minutes. Remarkably close to Earth's 24-hour day, close enough that early missions to Mars, including the rover teams at NASA's Jet Propulsion Laboratory, found it practical to schedule their work on Martian time during critical mission phases, gradually shifting their schedules by 37 minutes each day relative to Earth time, wearing special watches calibrated to the Martian sol rather than the Earth day. A Martian sol, the term used for a Martian day, is only slightly longer than an Earth day, but the accumulated drift, 37 minutes per day, eventually pushes a Martian schedule entirely out of phase with the Earth day around it. A small but genuinely disorienting experience for the people who have lived it. Mars is tilted on its axis at about 25 degrees, remarkably close to Earth's tilt of 23.5 degrees. And this similarity means that Mars experiences seasons in a broadly similar way to Earth. Both hemispheres take turns leaning toward the sun, producing summer in one hemisphere and winter in the other, then switching as the planet continues around its orbit. But because a Martian year is nearly twice as long as an Earth year, Martian seasons are also roughly twice as long. And because of Mars's elliptical orbit, the seasons are not symmetrical in length or intensity. Mars is closer to the Sun during southern hemisphere summer, meaning southern summers are shorter and warmer than northern summers, and southern winters are longer and colder than northern winters, a climate asymmetry with real consequences for how ice and dust distribute across the planet's surface. Now let's talk about the surface, because the surface of Mars is where things become truly extraordinary. Mars has a surface area of roughly 145 million square kilometers, about the same as Earth's total land area. No oceans, no seas, just land in all directions, for as far as any rover or lander has ever been able to look. And that land is, in the most literal sense, the most geologically dramatic terrain in the solar system. Mars is home to the tallest volcano in the solar system. It contains the longest and deepest canyon system in the solar system. It has vast, ancient impact craters that dwarf anything comparable on Earth or the Moon. And it has, written into its rocks and its valleys and its dried lake beds and its ancient river channels, the unmistakable record of a past that was far warmer and wetter than its frozen present. Olympus Mons is perhaps the single most striking geological feature on any planet we have visited. It is a shield volcano, broad and gently sloping, built up by billions of years of low-viscosity lava flows spreading outward from a central vent, and it is enormous by any standard we have available. Its base diameter is roughly 600 kilometers, approximately the size of the state of Arizona. Its peak rises about 22 kilometers above the surrounding volcanic plains, nearly 2.5 times the height of Mount Everest above sea level. The caldera at its summit, the collapsed depression where the volcanic vent sits, is 80 kilometers across and 3 kilometers deep. The outer edges of Olympus Mons are marked by dramatic cliffs, called the escarpment, rising as high as 8 kilometers above the surrounding lava plains in some places, meaning the boundary of the volcano is, in itself, taller than the highest mountain on Earth. From orbit, Olympus Mons is unmistakable, a vast, slightly elevated circular structure so large that, standing anywhere on its gently sloping flanks, you would have no visual sense of being on a mountain at all. The slope is only about 5 degrees on average. The volcano would simply look like a very slightly tilted plane, extending in all directions to a horizon that curves away at Martian distances. Only at the summit, approaching the enormous caldera, would the true nature of the structure become apparent. Why is Olympus Mons so much larger than anything on Earth? The answer lies in the difference between Martian and terrestrial geology. Earth's crust is divided into tectonic plates that move slowly across the mantle below, driven by convection. A volcano sitting over a hot spot in Earth's mantle doesn't stay in one place. The plate it's sitting on eventually drifts away, carrying the volcano with it, and the hot spot begins building a new volcano behind it. This is why the Hawaiian Islands form a chain. Each island is an old volcano that drifted away from the hot spot, with the currently active Big Island being the youngest, directly above the hot spot today. Mars, by contrast, has no plate tectonics, or at least none that have been active in billions of years. A Martian volcano sitting over a hot spot stays over that hot spot, and lava continues to pile up in the same location over billions of years, building a structure of genuinely planetary proportions. Olympus Mons represents what happens when you run a volcanic system for billions of years without ever moving the volcano away from its heat source. Running roughly along Mars's equatorial region, the Tharsis Plateau is a vast volcanic upland nearly the size of North America, raised several kilometers above the surrounding plains by billions of years of volcanic activity. The weight of the Tharsis Bulge is large enough that scientists believe it has slowly affected the orientation of Mars as a whole, a phenomenon called true polar wander, where the planet's rotation axis shifts gradually in response to large changes in the distribution of mass. The presence of Tharsis has been a dominant influence on Martian geology and perhaps on Martian climate for much of the planet's history. East of Tharsis, the land drops away into one of the most dramatic geological features in the solar system, Valles Marineris, named after the Mariner 9 spacecraft that first revealed it clearly in the early 1970s. This is a canyon system of truly planetary scale, stretching roughly 4,000 kilometers from end to end, reaching depths of up to 7 kilometers in its deepest sections, and spanning a width of up to 200 kilometers in some places. Laid across the United States, Valles Marineris would stretch from the Pacific coast to the Atlantic. The Grand Canyon, often invoked for comparison, is about 446 kilometers long and about 1.5 kilometers deep at its deepest, impressive on Earth, but dwarfed in every dimension by its Martian counterpart. The origin of Valles Marineris is somewhat different from the river-carved Grand Canyon. While water may have flowed through portions of it and modified its features, the main valley system is believed to have formed primarily through tectonic rifting, the stretching and splitting of the Martian crust as the Tharsis Bulge pushed up to the west, creating tensional fractures that eventually grew and deepened over billions of years. Portions of Valles Marineris show evidence of massive landslides, of ancient lake sediments, of materials deposited by flowing water, layered in ways that tell a complex and not yet fully decoded story of the canyon's long geological history. Beyond these extraordinary features, Mars also hosts two strikingly different hemispheres. The southern hemisphere of Mars is ancient, heavily cratered highland terrain, some of the oldest surface in the solar system, dating back nearly 4 billion years, preserving the record of the intense meteorite bombardment that characterized the early solar system. The northern hemisphere, by contrast, is predominantly low, smooth lowland plains, far less cratered, suggesting it's younger and has been resurfaced by volcanic and possibly other geological activity. The difference in elevation between the southern highlands and the northern lowlands averages several kilometers, and the boundary between them, sometimes called the crustal dichotomy, is one of the most dramatic and least fully explained features of the Martian surface. What caused one hemisphere to end up so much lower and smoother than the other remains actively studied and debated. One possibility, suggested by computer modeling, is that the northern lowlands were shaped by an enormous impact, perhaps the largest impact in the solar system's history, early in Mars's development. A collision so energetic it resurfaced the entire northern hemisphere and reset its geological clock, leaving the smooth, crater-sparse terrain we see today. If true, the northern lowlands of Mars are the scar of a collision with an object possibly as large as a dwarf planet, a wound the planet has carried for 4.5 billion years. There are also, scattered across the Martian surface, enormous ancient impact craters that speak quietly to the violence of the early solar system. Hellas Planitia in the southern hemisphere is one of the largest confirmed impact craters in the solar system, nearly 2,300 kilometers wide and more than 7 kilometers deep at its lowest point. Standing at the center of Hellas, you would be at the lowest point on Mars, more than 7 kilometers below the surrounding highland terrain, low enough that the atmospheric pressure at the crater floor is measurably higher than at the average surface level, still far too thin to breathe. but enough to make Hellas the location on Mars where liquid water would be most stable, if temperatures were warm enough to allow it. Chryse Planitia is another enormous ancient basin in the southern hemisphere, and Isidis Planitia in the northern, each one a scar from a collision that would have been catastrophic beyond imagining in human terms. One subtle but scientifically important detail of Martian geology is the prevalence of basalt across the surface. Martian rocks, examined by landers and rovers and analyzed through orbital spectroscopy, are overwhelmingly volcanic in character. Dark basalt and related volcanic rocks dominate the surface composition of much of the planet. This tells us that Mars's geological history has been dominated by volcanic activity rather than the tectonic plate recycling that constantly renews and diversifies Earth's crustal composition. Without plate tectonics to subduct old rock and expose fresh mantle material in new configurations, Mars's crust has remained broadly volcanic in character, with only localized variations driven by water chemistry, impact events, and wind transport. The color of Mars, that familiar, unmistakable reddish-orange, comes not from the basalt beneath, which is dark and gray, but from a thin coating of iron oxide dust that covers most of the surface. This dust has been redistributed by billions of years of wind across the entire planet, coating rocks, filling valleys, drifting into dunes. The underlying rock, where exposed by impacts or erosion, often appears much darker and grayer than the surface dust suggests. The famous red planet is, at its foundation, a dark gray volcanic world wearing a thin coat of rust-colored dust, like a fine, ancient patina laid on by time and the slow chemistry of iron oxidation. Let's talk about the Martian atmosphere, because it shapes everything about the planet's character: the cold, the dust, the impossibility of standing on the surface unprotected, the memory of what Mars once was. Mars's atmosphere today is thin, about 1% as dense as Earth's atmosphere at sea level, and composed almost entirely of carbon dioxide, roughly 95%. The remaining 5% is mostly nitrogen and argon, with trace amounts of oxygen, carbon monoxide, water vapor, and other minor gases. There is not nearly enough oxygen for a human to breathe. The atmospheric pressure at the Martian surface averages about 600 pascals, compared to about 101,000 pascals at Earth's sea level. This pressure is so low that liquid water cannot exist stably on the open Martian surface, even at temperatures above the freezing point. It would either evaporate nearly instantly or freeze, depending on conditions, rather than remaining liquid. The Martian surface temperature varies widely with latitude, altitude, and season, but the average surface temperature is approximately -60 degrees Celsius. At the equator, on a sunny afternoon in summer, temperatures can rise to around 20 degrees Celsius, briefly warm enough to feel pleasant by Earth standards, if you were somehow protected from the low pressure and the unbreathable air. But the same equatorial location, after sunset, will plunge to -70 degrees Celsius or colder because the thin atmosphere holds almost no heat after the sun goes down. Mars's atmosphere is too sparse to act as an effective thermal blanket, so the daily temperature swings on the surface are far more extreme than anything experienced on Earth. The thin atmosphere also provides very little shielding from solar radiation. Earth's atmosphere, combined with its magnetic field, provides substantial protection from the stream of energetic particles and ultraviolet radiation flowing from the sun. Mars has neither a meaningful atmosphere nor a global magnetic field. It lost its global magnetic field billions of years ago when its interior cooled and its core stopped generating the dynamo action that had once produced it. Without that protection, the Martian surface is bathed in levels of radiation significantly higher than anything experienced on Earth's surface, high enough that prolonged unprotected exposure would be dangerous. Future human explorers will need to spend significant time in shielded habitats or underground to manage the radiation dose they accumulate. What remains of Mars's atmosphere was once much thicker, much warmer, and much more capable of supporting liquid water on the surface. Over billions of years, that atmosphere was gradually stripped away by the solar wind, which erodes the upper atmosphere continuously, a process that accelerated dramatically when Mars lost its protective magnetic field. Scientists using the MAVEN spacecraft, which studied Mars's upper atmosphere for more than a decade after arriving in 2014, measured how the solar wind and solar storms strip gas from the planet into space. MAVEN's work showed that atmospheric escape increases during solar storms and helped quantify how a once thicker atmosphere could have been eroded over geological time. By working backward through these measurements and models, scientists have built a clearer, though still incomplete, picture of how much thicker the ancient atmosphere might have been and when conditions on the surface might have been warm and wet enough to support liquid water. The answer, broadly, is that the transition from a warm, wet Mars to the cold, dry Mars we know today happened gradually over the first 1.5 billion or 2 billion years of the planet's history, with the last liquid water on the surface disappearing perhaps 2 to 3 billion years ago. Though brief, localized episodes of liquid water may have occurred more recently than that, driven by impacts, volcanic activity, or brief climate fluctuations. The composition of the Martian atmosphere also creates a survival challenge separate from the simple absence of oxygen. The dominant carbon dioxide would cause rapid suffocation if inhaled directly, and the trace perchlorate compounds found widely in Martian soil are toxic to the human thyroid if ingested in significant quantities. Mars is not merely inhospitable in the way a cold mountain is inhospitable. It is chemically incompatible with unprotected human biology at nearly every level simultaneously: pressure, temperature, radiation, composition. Surviving on Mars requires not just warm clothing, but a complete rethinking of how a livable environment is built from the ground up. Yet the atmosphere is also a resource. Carbon dioxide can be processed to extract oxygen, and this is what NASA's MOXIE experiment aboard Perseverance successfully demonstrated on the Martian surface. MOXIE completed its Mars mission in 2023 after producing a total of about 122 grams of oxygen, with individual runs showing that oxygen could be made from Martian atmospheric carbon dioxide at high purity. The amounts were modest, grams, not tanks, but the principle was demonstrated. A scaled-up version of this technology operating continuously could produce meaningful quantities of oxygen for breathing and for rocket propellant on a human mission, dramatically reducing the mass that would need to be carried from Earth. The resource question is not a side issue for Mars. It is central. A spacecraft can bring everything it needs for a robotic mission because the robot is small and the mission is limited. A human mission cannot be treated the same way. The mass of water, oxygen, fuel, spare parts, shielding, food, and equipment needed for a multi-year journey and surface stay becomes enormous very quickly. That is why in situ resource utilization, using what Mars already provides, is one of the core ideas behind serious human mission planning. Mars provides carbon dioxide in the atmosphere, water ice in the subsurface and polar regions, sunlight for solar power, wind that is too thin to be useful for ordinary wind turbines, and rock that could eventually be used as construction material or radiation shielding. None of these resources is easy to use. Carbon dioxide must be processed. Ice must be located, accessed, purified, and protected from sublimation. Dust can coat solar panels and damage seals. Perchlorates complicate soil handling. But each resource that can be used locally reduces the amount that must be launched from Earth, and every kilogram not launched from Earth changes the architecture of a mission. One of the defining features of Martian weather is its dust. Mars is a dusty world, covered in fine iron oxide particles, rust, essentially, that give the planet its characteristic reddish color. The iron oxide in Martian dust is the same compound that makes rust red on Earth, formed over billions of years through chemical reactions between the Martian rocks, water, and what oxygen the atmosphere contained. This fine, reddish dust is everywhere, coating the rocks, blowing in the thin winds, suspended in the atmosphere in quantities sufficient to give the Martian sky a characteristic butterscotch or pinkish tin color rather than the deep blue that Earthlings associate with daytime skies. The Martian sky, viewed from the surface, is not blue by day. It takes on shades ranging from pinkish gray to pale tan depending on how much dust is suspended in the atmosphere at any given time. Photographs from every lander and rover on Mars confirm this. The sky is pale and dust-colored under most conditions, with only the finest atmospheric conditions, in periods of exceptionally low dust loading, approaching a pale blue. Sunrise and sunset on Mars, by contrast, produce blue-tinted skies around the sun, the opposite of Earth's red-orange sunsets, because the dust scatters light in a way that preferentially puts blue light near the sun and redder tones further away. Mars experiences dust devils, small, spinning columns of air similar to but often larger than the dust devils that occur in deserts on Earth, on a frequent basis, lifted by convective heating of the surface during sunny afternoons. Rovers have photographed hundreds of dust devils moving across the Martian plains, and Perseverance has even recorded audio of one passing nearby, the first sound of a Martian dust devil ever captured. These dust devils play a role in the global dust budget, lifting material from the surface and lofting it into the atmosphere, where it can remain suspended for extended periods. More dramatically, Mars is subject to planet-encircling dust storms, events with no counterpart on Earth, where dust suspended in the Martian atmosphere spreads across the entire planet over weeks or months, reducing sunlight at the surface by 80% or more and dramatically cooling the surface while warming the upper atmosphere. These global dust storms don't occur every year, but when they do, they transform the planet completely. They have ended at least one mission prematurely. The Opportunity rover, designed to survive on solar power, was unable to charge its batteries sufficiently during the 2018 global dust storm, and contact was lost before the storm cleared. NASA made repeated attempts to recontact Opportunity for months after the storm ended, broadcasting the rover's wake-up command over 800 times before officially declaring the mission over in February 2019, after nearly 15 years of operation far beyond its original 90-day design lifetime. The origin and triggering mechanism of global dust storms on Mars is still not fully understood. They seem to begin as regional storms that, under certain conditions, grow and spread around the planet in a self-reinforcing cycle. The dust heats the atmosphere where it's suspended. The heated atmosphere generates winds. The winds lift more dust, which spreads and heats more atmosphere. But why some regional storms grow into global events while others don't is a question that current models can't reliably predict. Each global storm that occurs is studied intensively, and each one adds more data to the slowly accumulating picture of how Mars's weather system operates. Mars has 2 moons. They are among the strangest objects in the solar system. Small, irregular, dark, and so different from our own moon that they require a completely different origin story, or rather, an origin story that is itself still not fully settled. Phobos, the inner and larger of the two, is roughly 27 kilometers across at its longest dimension, and Deimos, the outer moon, is only about 15 kilometers at its longest. Neither is even remotely spherical. Both are lumpy, irregular shapes, looking more like elongated potatoes or asteroids than like the round, elegant moon that circles Earth. Both are very dark, with surfaces that reflect only a few % of the light that hits them, far less reflective than most rocky surfaces, more similar in color and composition to the dark carbonaceous asteroids of the outer asteroid belt than to ordinary rocks. This similarity to outer asteroid belt material is one of the clues that has led some scientists to propose that Phobos and Deimos are captured asteroids, objects that once traveled through the asteroid belt and at some point in the past had their orbits perturbed by Jupiter's gravity, sending them on new trajectories that eventually brought them close enough to Mars to be captured by the planet's gravity. The problem with this hypothesis is that captured asteroids typically arrive with highly elliptical, often tilted orbits, while Phobos and Deimos both orbit Mars in nearly circular, nearly equatorial paths, the kind of well-behaved orbits that don't naturally result from a capture event without some additional mechanism to circularize them. An alternative hypothesis suggests the moons formed from debris produced by a giant impact on Mars early in the solar system's history, similar in broad concept to the giant impact hypothesis for Earth's moon. A large object striking Mars could have thrown material into orbit that then coalesced into the two small moons we see today. This scenario naturally produces circular, equatorial orbits, and recent modeling has suggested it may be more consistent with the moon's observed properties than the capture hypothesis. The truth may lie somewhere between these scenarios, or in a third option not yet fully developed. Future missions may help resolve the question. Japan's Martian Moons Exploration Mission, or MMX, is planned for launch in Japanese fiscal year 2026 and is designed to study Phobos and Deimos, land on Phobos, collect a surface sample, and return it to Earth. If successful, it could provide the first laboratory sample from a Martian moon and a direct test of whether Phobos is captured primitive material, impact debris from Mars, or something more complicated. Phobos has one property that makes it particularly notable among all the moons in the solar system. It is slowly spiraling inward toward Mars, orbiting so close to the planet, only about 6,000 kilometers above the Martian surface, closer than any other known moon to its parent planet. Phobos is subject to tidal forces that are gradually sapping its orbital energy, causing it to inch closer to Mars by about 2 centimeters per year. At this rate, in approximately 30 to 50 million years, Phobos will cross the Roche limit, the distance within which Mars's tidal forces exceed the moon's own self-gravity, and begin to break apart. The debris may form a thin ring around Mars for a time, or rain down onto the Martian surface in a series of impacts, or some combination of both. Phobos is, in other words, a moon with a finite and measurable end date, slowly falling to its destruction in a time frame that is short by geological standards, though still comfortably beyond any human concern. From the Martian surface, Phobos rises in the west and sets in the east, the opposite of the Sun and Deimos, because it orbits Mars faster than Mars rotates, lapping the planet's own rotation about 3 times per Martian day. It crosses the sky so quickly that a patient observer could watch it visibly move across the sky in the course of a single hour. Deimos, orbiting farther out and more slowly, moves in the same direction as the Sun and sets in the west, crossing the sky over the course of about 2.5 Martian days. Both moons, from the surface, appear small, Phobos about 1/3 the angular diameter of our moon, Deimos barely a bright star-like, too small to completely block the sun during a solar eclipse, producing instead a brief transit of a dark oval shape crossing the solar disk. Both Curiosity and Perseverance have photographed these transits, and the images have a quiet, alien beauty, a small, lumpy, irregular shape moving across the face of a sun that appears slightly smaller than it does from Earth. The most important story written into the geology of Mars is also, in many ways, the saddest one, the story of water. Mars was not always the frozen desert it is today. The geological record of the Martian surface tells a clear story of a planet that, in its earliest epochs, had liquid water in abundance, rivers, lakes, possibly shallow seas covering portions of the northern lowlands, and a climate warm and wet enough to sustain that liquid water for long enough to leave behind unmistakable geological signatures. The evidence is everywhere, once you know how to look for it. Ancient river valleys, carved into the southern highlands, branch and merge like river systems on Earth, shaped by flowing water rather than any other geological process. Some of these valleys are wide and deep, suggesting large volumes of water flowing over extended periods. Others show the characteristic branching patterns of drainage networks, smaller tributaries feeding into larger channels, exactly the pattern produced by rainfall and runoff in a landscape. The existence of branching valley networks on Mars is considered strong evidence that rainfall occurred at some point in the planet's history, not just occasional melt events, but sustained precipitation over long enough periods to carve a drainage landscape. More dramatic are the outflow channels, enormous, catastrophic flood features that dwarf anything comparable on Earth. Channels like Cassae Vallis and Ares Vallis are hundreds of kilometers wide and show the unmistakable signatures of enormous floods: teardrop-shaped islands, streamlined hills, scoured bedrock. The floods that carve these channels are estimated to have been among the most violent geological events in the solar system's history, releasing water at rates thousands of times greater than the Amazon River, capable of carving channels hundreds of kilometers wide and many meters deep in timescales of perhaps days to weeks. These floods may have been triggered by volcanic activity melting subsurface ice, or by impacts releasing stored water, or by other mechanisms that released enormous quantities of water suddenly and catastrophically. In the years since the first Mars orbiters and landers, the evidence for past water has accumulated steadily. The CRISM spectrometer aboard the Mars Reconnaissance Orbiter has identified clay minerals, phyllosilicates, at many locations across the Martian surface, clay minerals that form only through prolonged contact with liquid water. The presence of sulfate minerals at other locations points to a later phase of Mars's geological history, when water was present but more acidic. The Mars exploration rovers Spirit and Opportunity found direct geological evidence of water-altered rock chemistry at their landing sites. Iron-rich spherules called blueberries scattered in the rock at Opportunity's Meridiani Planum site, formed by mineralization in ancient groundwater systems. Outcrops of layered sedimentary rock at Opportunity's Endurance crater that could only have been deposited in standing water, and sulfate-rich rocks in geological sequences suggesting ancient evaporation events, like the patterns left when a lake dries up and its dissolved minerals precipitate out. Curiosity, operating in Gale Crater since 2012, has found even more compelling evidence. Gale Crater, selected precisely because orbital observations suggested it once contained a lake, has given up geological confirmation of that hypothesis. Finely layered sedimentary rocks, the kind that form only in standing water over long periods. Mineral assemblages consistent with lake environments, and organic molecules, carbon-containing compounds, preserved in ancient mudstone deposits. Curiosity's instruments have directly detected organic molecules in billion-year-old Martian rock, molecules that may or may not have a biological origin, but that demonstrate the planet's rocks have preserved chemical information across immense timescales. Perseverance, exploring Jezero Crater since 2021, has found further evidence of an ancient lake and delta system at its landing site. The crater contains what appears to be an ancient river delta, a fan-shaped deposit of sediment built up where a river once flowed into a lake and slowed, dropping its sediment load in the classic triangular form that river deltas produce on Earth. Perseverance has been systematically collecting rock core samples from this ancient delta, sealed in sample tubes that are being carefully cached on the surface for a future sample return mission to bring back to Earth for detailed laboratory analysis. Those samples, chosen specifically from the rocks most likely to have preserved evidence of ancient habitable environments, and most likely to preserve any biosignatures if life ever existed there, represent what may be the most scientifically significant collection of extraterrestrial material since the Apollo astronauts brought lunar rocks back from the moon. Mars today still has water, but in forms inaccessible on the surface. The polar ice caps, which we'll come to shortly, contain enormous quantities of water ice, mixed with frozen carbon dioxide. Subsurface ice has been detected extensively across the middle and high latitudes of Mars, detected through radar sounding instruments aboard orbiters, through the thermal signatures of the near surface, and through direct observation at the Phoenix lander site, where the lander's thruster exhaust exposed chunks of subsurface ice that were photographed before they sublimated in the thin Martian atmosphere. And there may be liquid water deep underground, where geothermal heating keeps temperatures above freezing despite the extreme cold at the surface. Radar data from the MARSIS instrument aboard Mars Express suggested the possible existence of a subglacial lake beneath the south polar ice cap, an interpretation that remains debated, with some scientists finding the evidence compelling and others questioning whether it could be produced by other mechanisms. But if confirmed, it would represent the first confirmed liquid water on Mars today. Mars is also a world of hidden ice, and hidden ice changes the practical and scientific meaning of the planet. From orbit, instruments have found hydrogen signatures that point to widespread subsurface water ice, especially at middle and high latitudes. Fresh impact craters sometimes expose bright material that fades as it sublimates, strongly indicating shallow ice just beneath the surface. Radar observations reveal buried glaciers and ice-rich deposits protected beneath layers of dust and debris. In some regions, features called lobate debris aprons flow outward from mesas and valley walls, shaped like slow-moving glaciers on Earth, except that on Mars the ice is often covered by a protective blanket of rock and dust. This buried ice matters for climate history because it records changing obliquity, the tilt of Mars's axis. Mars does not have a large stabilizing moon like Earth. Its axial tilt varies chaotically over long timescales, shifting the distribution of sunlight across the planet. When the tilt is higher, polar ice can become unstable and migrate toward lower latitudes. When the tilt changes again, that ice can be buried, preserved, or redistributed. The landscape of Mars is therefore partly a frozen record of orbital cycles. Ice moved, buried, exposed, and moved again as the planet's orientation changed over hundreds of thousands and millions of years. For future human missions, buried ice is one of the most important resources on the planet. Water is life support, radiation shielding, agriculture, chemistry, and propellant feedstock if split into hydrogen and oxygen or combined with atmospheric carbon dioxide to make methane. A landing site near accessible ice would change mission design dramatically, but the ice cannot simply be assumed. It must be mapped, confirmed, mined, purified, and handled in an environment where exposed ice can vanish into the thin air. A good Mars landing site for humans is therefore not only scientifically interesting and safe to land on, it must also be close to resources without placing astronauts in terrain too dangerous to operate. This is one of the reasons Mars exploration has become so detailed. The future of Mars depends on maps of ice, minerals, slopes, dust, radiation, rock abundance, landing hazards, and communications geometry. Before people ever arrive, robots and orbiters are already turning Mars from a mysterious red disk into a navigable world. The polar ice caps of Mars are among the most visually striking features of the planet when viewed from orbit, and they are far more complex than simple deposits of frozen water or carbon dioxide. Each cap has two distinct components. The permanent, residual polar caps are composed primarily of water ice, thick and stable year-round, the Martian equivalent of Earth's polar glaciers. The seasonal caps are composed primarily of frozen carbon dioxide, dry ice, that condenses out of the atmosphere during the long Martian winter at each pole, growing to cover large regions of the surrounding terrain before sublimating back into the atmosphere each spring. The North Polar region changes dramatically with the seasons. Carbon dioxide frost spreads outward during winter and retreats again in spring, while the residual cap of water ice remains through the year. The permanent northern water ice cap is roughly 1,000 kilometers across, but the seasonal frost cover can extend much farther across the surrounding terrain. Beneath and around the residual cap lie the North Polar layered deposits, thousands of layers of ice and dust that record repeated changes in Martian climate. These layers are not simple annual tree rings. Many reflect longer climate cycles driven by changes in Mars's tilt, orbit, dust loading, and ice migration. Visible in spectacular cliff exposures around the cap's edges, the layered deposits are one of the planet's most important climate archives, preserving a record that may stretch back millions of years. The South Polar Cap differs from the North in several ways. It is smaller and colder, partly because the South Pole experiences its winter during Mars's aphelion, when Mars is farthest from the Sun, making southern winters longer and colder than northern winters. The South Polar Cap retains a thin, permanent deposit of frozen carbon dioxide over its water ice core, unlike the North Cap, which loses all its carbon dioxide frost each summer. And the South Cap is the location of the suspected subglacial lake detected by MARSIS, sitting beneath roughly 1.5 kilometers of ice. If the interpretation of the radar data is correct, both caps show remarkable surface features. The North Cap surface is carved into a spiral pattern of troughs and mesas, shaped by winds that persistently blow in specific directions relative to the cap's geometry, sculpting the ice in a way that looks almost designed. The South Cap has a landscape of bizarre round pits and holes in the carbon dioxide ice, a terrain sometimes called Swiss cheese by mission scientists for its appearance, created by sublimation of the dry ice in patterns controlled by the slope and orientation of the surface. These features change from year to year as the carbon dioxide deposits grow and recede, making the polar regions among the most dynamically active environments on the Martian surface. Mars lost its global magnetic field billions of years ago, and this loss is one of the most consequential events in the planet's history, shaping everything that followed. When Mars first formed, like Earth, it likely had a global magnetic field generated by convection in its liquid iron core, a dynamo similar to the one that generates Earth's magnetic field today. This field would have provided significant protection from the solar wind, helping Mars retain the thicker, warmer atmosphere that evidence suggests it once had. The geological record suggests this global magnetic field was present for perhaps the first 500 million years or so of Mars's history, and then disappeared. The reason the dynamo stopped is not fully understood, but it may relate to Mars being smaller than Earth, and therefore cooling more rapidly. A smaller planet loses its internal heat faster, and as the Martian core cooled, at some point the convection driving the dynamo weakened and eventually ceased. Without the dynamo, the magnetic field collapsed. Without the magnetic field, the solar wind had direct, unimpeded access to the upper atmosphere, gradually stripping it away through a process called atmospheric escape, which has continued, slowly, to this day. One of the intriguing legacies of Mars's ancient magnetic field is found in the oldest rocks of the Southern Highlands. Magnetized rocks, carrying a frozen imprint of the magnetic field that existed when they formed and cooled billions of years ago. This remnant magnetism, detected by the Mars Global Surveyor spacecraft in the 1990s, is organized into parallel bands of alternating magnetic polarity, a pattern remarkably similar to the magnetic stripes found on Earth's seafloor, which record the reversals of Earth's magnetic field as tectonic plates spread apart from mid-ocean ridges. Some scientists have taken this as evidence that Mars may have had a primitive form of plate tectonics in its earliest era, though this remains controversial. Whether or not Mars ever had true plate tectonics, the magnetized bands in its ancient crust are a fossil record of a time when Mars was a magnetically active, more Earth-like world. The InSight lander, which operated on Mars from 2018 until late 2022, was designed specifically to study the Martian interior. Using an extremely sensitive seismometer, InSight detected hundreds of Mars quakes during its mission, vibrations within the Martian crust produced by geological stresses, meteorite impacts, and possibly residual internal activity. These seismic readings have allowed scientists to build the first direct model of Mars's interior structure from below. The thickness and composition of the crust, the properties of the mantle, and characteristics of the core. Preliminary results suggested Mars has a surprisingly large, liquid core, larger than expected, and a crust that is thicker than older models had predicted. These findings are still being analyzed and interpreted, but InSight's data represents a fundamental advance in our understanding of Mars's deep interior. The first time seismology has been used to probe another planet's internal structure from its own surface. The Martian interior is another part of the planet that has become more real in the last few years. Before InSight, the deep interior of Mars was inferred indirectly from gravity, topography, meteorites, and models. InSight changed that by placing a seismometer directly on the surface and listening. Mars turned out to be seismically active enough to study, though not nearly as restless as Earth. The lander detected hundreds of Mars quakes, some produced by internal stresses and others linked to meteorite impacts. By measuring how seismic waves traveled through the crust, mantle, and core, scientists could begin building the first interior map of another rocky planet based on direct seismic data. The results were revealing. Mars has a liquid core, large relative to the planet's size, with light elements mixed into iron and nickel. Its crust is thicker and more variable than simple older models suggested. Its mantle has cooled and stiffened, but the planet is not without internal motion or stress. Some Mars quakes appear to come from the Cerberus Fossae region, a young volcanic and tectonic area that may still retain residual heat. This does not mean Mars is volcanically active in the Earth-like sense, with eruptions expected at any moment. But it does mean the planet's interior is not simply a cold stone ball. This matters for habitability because internal heat is one of the possible ways to maintain liquid water below the surface. A planet that is dead at the surface may still have chemically interesting environments underground. Water moving through warm rock can create chemical gradients. Minerals can be altered. Hydrogen can be produced. On Earth, deep subsurface microbes live in environments that never see sunlight, powered by chemical reactions between water and rock. If Mars has any present-day habitable environment, it is far more likely to be underground than on the surface. But the subsurface is also the hardest place to reach. Rovers can scrape, drill shallow holes, and analyze exposed rocks, but a truly protected environment may lie meters, hundreds of meters, or even kilometers below the surface. That is why Mars exploration remains incomplete despite decades of missions. We have mapped the surface beautifully. We have sampled shallow materials. We have listened to the interior. But the deep subsurface, perhaps the most important place for present-day life, remains mostly beyond our reach. The ancient climate problem is one of the most important unresolved questions about Mars. The geology says water flowed. The valley networks, deltas, clays, lake beds, and sedimentary rocks are not subtle evidence. They point to liquid water at the surface, sometimes for extended periods. But climate models struggle with the same problem again and again. The young sun was fainter than it is today, and even a thicker carbon dioxide atmosphere does not always warm early Mars enough to keep liquid water stable over broad regions for long periods. This is the Martian version of the faint young sun problem. Several solutions have been proposed. A thicker atmosphere could have provided more greenhouse warming. Hydrogen mixed into a carbon dioxide atmosphere could have amplified the greenhouse effect. Methane, sulfur gases, high-altitude ice clouds, impact-generated steam atmospheres, volcanic pulses, or episodic climate swings may have warmed Mars intermittently rather than continuously. The correct answer may not be a single warm and wet Mars, but a sequence of habitable windows, periods when water flowed, lakes formed, sediments accumulated, and chemistry became interesting, separated by colder and drier intervals. This nuance matters for life. A planet does not need to be Earth-like for billions of years to be scientifically important. It needs environments where liquid water, energy, and useful chemistry coexist long enough for prebiotic chemistry or biology to matter. Mars may have offered those environments early, locally, and repeatedly, even if it was not a stable blue world. Mars also forces scientists to think carefully about what counts as evidence. A dried river valley is evidence of flowing water, but not by itself evidence of life. Clay minerals are evidence of water-rock interaction, but not of biology. Organic molecules are evidence of carbon chemistry, but not of living organisms. Methane, if detected reliably, can be produced by life, but it can also be produced by geology. A texture in a rock can look biological and still form through non-biological chemical reactions. A chemical gradient can supply energy for microbes and still never have been used by microbes. This is why Mars science is cautious even when discoveries sound dramatic. A potential biosignature is not a biosignature confirmed. A habitable environment is not an inhabited environment. Organic carbon is not fossil life. The distinction can be frustrating because the human mind wants narrative closure. Water plus organics plus energy should mean life. But science has to move more carefully. The most important discoveries on Mars often matter precisely because they narrow the uncertainty without erasing it. The Chiava Falls rock illustrates this modern caution. Perseverance found features in a rock from Jezero crater that NASA described as a potential biosignature. Chemical and textural patterns that, on Earth, can be associated with microbial activity, preserved in a setting that once held water. That is important. It is one of the strongest leads Mars science has produced. But it is not a detection of life. Non-biological reactions can also create surprising mineral and organic patterns. Without laboratory analysis on Earth, with instruments far more powerful than anything a rover can carry, the safest scientific statement remains that Chiava Falls is a compelling target, not an answer. This kind of restraint is not weakness. It is what keeps the search credible. The history of Mars is full of tempting signals. The canals that were not canals, the Viking biology results that were most likely chemistry, the meteorite LH-84001 with structures and minerals once interpreted by some as possible fossil microbes, methane detections that vary between instruments and campaigns, subsurface water interpretations that remain debated. Mars repeatedly teaches the same lesson. The planet is interesting enough that ambiguity is expected, and the answer to ambiguity is better evidence, not louder certainty. The question of life on Mars is perhaps the most discussed most debated, and most carefully studied question in planetary science. It has shifted significantly in character over the past century, but it has never gone away. In the late 19th century, the Italian astronomer Giovanni Schiaparelli reported observing what he described as canali on Mars, narrow, linear features crossing the planet's disk, a word meaning channels or grooves, but translated into English as canals, with all the engineering connotations that word implies. The American astronomer Percival Lowell, working at his private observatory in Arizona in the 1890s and early 1900s, elaborated these observations into an elaborate, fully developed vision of a dying Martian civilization, constructing a planet-wide irrigation network to bring water from the polar ice caps to the parched equatorial regions where their crops grew. Lowell's vision captured the public imagination enormously, fueling decades of science fiction and cultural fascination with Mars, and it wasn't fully put to rest until the first Mars orbiters of the 1960s revealed that the canals simply did not exist. They were an optical illusion, the human brain's tendency to connect faint, ambiguous surface features into straight lines when looking at the limit of a telescope's resolution. But even before the telescope era, Mars held a particular place in human attention. Ancient Egyptian astronomers were tracking Mars's motion against the stars more than 3,000 years ago. Babylonian records detail its behavior over centuries. Ancient Greek and Roman astronomers incorporated Mars into their cosmological models, associating it with the god of war, Ares in Greek, Mars in Latin, presumably because of its blood-red color, a color that has been inspiring human imagination and myth-making for as long as there have been human eyes to see it in the night sky. In the 17th and 18th centuries, as telescopes improved, Mars began revealing itself in more detail. Christian Huygens, the same astronomer who identified Saturn's rings, sketched surface features on Mars in 1659 and estimated the length of its day. Giovanni Cassini made further observations in the 1660s. William Herschel, who discovered Uranus in 1781, studied Mars's polar caps in the 1780s and correctly inferred that Mars had a tilted axis similar to Earth's, producing seasons. Each generation of astronomers who pointed improving telescopes at Mars found it more interesting, more Earth-like in certain ways, and more frustrating in its refusal to reveal its surface clearly through the turbulent layers of Earth's own atmosphere. The Hubble Space Telescope, placed above Earth's atmosphere, has provided some of the finest Earth-based views of Mars, particularly during oppositions when Mars is closest to Earth. But the true transformation in our understanding came not from better telescopes on Earth, but from spacecraft. When the Mariner 4 spacecraft flew past Mars in 1965 and sent back the first close-up images of its surface, cratered, cold, moon-like terrain, the disappointment in some quarters was genuine. Mars had gone, in a single flyby, from a possible home of ancient civilizations to an apparently dead, airless world. 21 photographs, each one painstakingly transmitted as numerical data and reconstructed on Earth, showed a heavily cratered landscape with no sign of the canals, the cities, or even the vegetation some had hoped to find. That disappointment was real but premature. Mariner 9, arriving in orbit in 1971, the first spacecraft ever to orbit another planet, revealed a Mars the brief Mariner 4 flyby images had completely missed. Mariner 9 arrived during a global dust storm, its cameras initially showing nothing but a featureless orange haze. But as the storm cleared over the following weeks, a completely different Mars emerged. Enormous volcanoes, including what would eventually be identified and named Olympus Mons, rising above the subsiding dust. The dramatic gash of Valles Marineris, stretching across the equatorial region in a geological feature with no comparison on Earth. Ancient river valleys in the southern highlands, unmistakably shaped by flowing water. A Mars that was not the simple, cratered wasteland of the Mariner 4 images, but a geologically complex world with a rich and varied history. Mariner 9's mission ran for nearly a year, transmitting more than 7,000 images, and essentially created the modern map of Mars. Many of the features it identified and named, Olympus Mons, Valles Marineris, the Tharsis region, have remained in use ever since, and the planetary scientists of today are still working to understand the features that Mariner 9 revealed for the first time. The Viking missions of 1976 were in many ways the most ambitious Mars program ever mounted. 2 orbiters and 2 landers traveled to Mars, with the landers touching down on the Martian surface in July and September of that year. The images Viking returned of the Martian surface, rocky plains stretching to a horizon remarkably similar in distance to Earth's, a butterscotch sky, reddish soil, were some of the most extraordinary photographs in the history of space exploration. For the first time, humanity was seeing the surface of Mars, not as a telescopic blur, but as a real place, photographed in color and detail from the ground. Viking's biology experiments produced results that have been discussed and debated for nearly 50 years. The labeled release experiment, which added water and nutrients to Martian soil and then monitored gas release, produced a positive signal, a spike in gas release that looked exactly like what would happen if soil bacteria metabolized the nutrients. This created enormous excitement at the time. But another Viking experiment, the gas chromatograph mass spectrometer, which searched directly for organic molecules in the soil, found none above its detection limits. Without organic molecules in the soil, most scientists concluded living organisms were very unlikely. The consensus interpretation attributed the labeled release result to perchlorates and other reactive chemical compounds in the Martian soil, producing a chemical rather than biological positive signal. The Viking biology results remain a subject of occasional revisitation by scientists. Some researchers have argued over the decades that the chemical explanation doesn't fully account for the Viking data, and that the question deserves another look with modern instruments. The consensus view has maintained that the chemical hypothesis is more parsimonious, and that the appropriate next step is more investigation, which is exactly what the rover missions of the 21st century have been designed to provide. The broader question of life on Mars, whether it ever existed, whether any trace of it remains, has evolved significantly from the simple Viking-era framing of "Does life exist on Mars today?" The modern scientific consensus, shaped by decades of improved understanding of Mars's geological and climate history, has reframed the question in 2 separate and important ways. The first asks whether life might exist today in protected subsurface environments, deep underground where geothermal heat, liquid water, and chemical energy might still provide the conditions for microbial survival, entirely shielded from the radiation and cold of the surface. The second asks whether life might have existed in the ancient past, during the warm, wet early Mars, and whether any biosignature of that ancient life might be preserved in rocks that have remained largely undisturbed for billions of years. Planetary protection sits over all of this like a quiet ethical constraint. Mars is both a place we want to study and a place we might contaminate by studying it. Terrestrial microbes are hard to eliminate completely. Spacecraft are cleaned, sterilized, assembled in controlled environments, and tested under strict protocols, but biology on Earth is persistent. If a future mission drills into a protected Martian subsurface environment and accidentally carries Earth organisms with it, the scientific damage could be enormous. A later detection of life would immediately face the question, is this Martian, or did we bring it? The reverse question is less likely but still taken seriously. If Martian samples come to Earth, they must be contained until scientists are confident they pose no biological hazard. This is not because anyone expects dangerous Martian life. It is because responsible exploration does not assume safety when the evidence is incomplete. The search for life requires curiosity, but it also requires restraint. Both questions remain open. The first is very difficult to answer with current technology, since reaching deep subsurface environments on Mars requires drilling capabilities far beyond anything yet deployed, and detecting life at depth would require either bringing samples to the surface or sending instruments down to where the life is. The second is the focus of Perseverance's sample collection campaign and of the broader Mars sample return effort, though that program has been under major redesign, with cost, schedule, and architecture still being reassessed. If and when those samples arrive in Earth laboratories, they could move the question of ancient Martian life from suggestive rover evidence to the much sharper scrutiny of terrestrial instruments. What Curiosity and Perseverance have found in the meantime has been extraordinary, even short of life detection. Curiosity's discovery of complex organic molecules preserved in 3-billion-year-old Martian mudstone was a watershed moment, demonstrating not only that organics were present in ancient Mars environments, but that the preservation chemistry of Martian rock is capable of protecting those molecules across geological timescales comparable to or exceeding the oldest preserved biosignatures on Earth. Perseverance's investigation of the Jezero Delta has reinforced this picture, finding abundant organic material in the delta sediments and demonstrating that the ancient lake environment that deposited them was not a brief or marginal environment, but a sustained, chemically varied system that persisted for geologically significant timescales. Mars sample return remains one of the most scientifically important and logistically difficult goals in planetary exploration. The basic idea is simple to describe and extremely hard to execute. Collect the sealed sample tubes Perseverance has prepared, launch them from the Martian surface, capture them in Mars orbit, and return them safely to Earth. In practice, the program has faced major cost, schedule, and architecture challenges, and NASA has been reassessing how to return the samples in a way that is technically realistic and financially sustainable. That uncertainty should not be hidden. It is part of the story, but the scientific value of the samples remains enormous. A receiving facility on Earth would operate under strict containment protocols, treating the Martian samples with exceptional care, not because dangerous Martian biology is considered likely, but because planetary protection requires caution when moving material between worlds. If delivered to Earth laboratories, the samples could be studied by instruments far too large and delicate to send to Mars, instruments that can identify individual molecules, measure isotopic ratios with extraordinary precision, image structures at the nanometer scale, and perform chemical analyses that take weeks or months in the best laboratories in the world. More recent analyses have made the organic chemistry story even more interesting. Curiosity's sample analysis at Mars Instrument has identified a broader and more diverse suite of carbon-containing molecules than earlier Mars missions could detect, including compounds never before seen on Mars. Perseverance, using its SHERLOC instrument, has also found complex organic carbon in fine-grained rocks in Jezero's Neretva Vallis region, including samples such as Chiava Falls and Valhalla Glades. These detections do not prove life. That point matters. Organic carbon can form through biological processes, but it can also form through non-biological chemistry involving water, rock, heat, and meteoritic delivery. The importance of these discoveries is subtler and more powerful. Mars can preserve complex carbon chemistry in rocks that formed in ancient watery environments, exactly the kind of setting where a future laboratory analysis might be able to separate biology from non-biology more clearly than a rover can. If those samples contain no biosignatures, that result would itself be scientifically significant, evidence that whatever happened in Jezero crater with all its warm lake conditions and organic chemistry, did not produce detectable life, at least not of a kind that left a signature in these particular rocks. If they contain something ambiguous, patterns in the chemistry or mineralogy that are consistent with biology but not definitively biological, the result will launch decades of further investigation to determine what it means. And if they contain something unambiguous, a chemical or structural signature that can only be explained by biological processes, the implications for our understanding of life's place in the universe would be extraordinary in ways that are genuinely difficult to fully imagine from this vantage point. The honest answer about life on Mars, as of today, remains, we don't know. But we are asking better questions with better instruments than at any previous point in history. Perseverance continues to collect and study carefully chosen rocks. Mars sample return remains scientifically central, even while its architecture is being reworked. Rosalind Franklin is designed to drill below the radiation-damaged surface, and every future mission, whether to Mars itself or to other potentially habitable worlds, brings lessons back to this central question. How do we recognize life when the evidence is old, altered, and difficult? Another important future mission is ESA's Rosalind Franklin rover, part of the ExoMars program, now targeting launch in 2028. Its scientific importance comes from a capability no previous Mars rover has had, a drill designed to reach as deep as 2 meters below the surface. That matters because the Martian surface is exposed to radiation and oxidizing chemistry that can destroy or alter organic molecules over time. A sample from 2 meters down is not guaranteed to contain preserved biosignatures, but it is protected far better than surface dust and rock. Rosalind Franklin is therefore designed to look for signs of past or present life in a way that complements Perseverance rather than duplicating it. Not by caching samples for Earth return, but by reaching below the hostile surface layer and analyzing the material directly on Mars. The reason Mars can be told this way, as a history rather than a set of facts, is that each mission changed the planet. Mariner 4 removed the old fantasy of canals and cities. Mariner 9 restored complexity by revealing volcanoes, canyons, and dried valleys. Viking gave Mars a surface and a color, and introduced the life detection question in a form that still echoes. Mars Global Surveyor mapped the planet with a precision impossible before it and found crustal magnetism that preserved evidence of an ancient dynamo. Mars Odyssey mapped hydrogen near the surface, helping reveal the widespread presence of buried ice. Mars Express brought European science to the planet and continues to contribute to the debate over subsurface water and atmospheric chemistry. The Mars Reconnaissance Orbiter gave researchers mineral maps, high-resolution images, and the ability to select landing sites with extraordinary confidence. Each rover then made Mars more local. Spirit found altered rocks in the Columbia Hills. Opportunity spent years reading the history of water at Meridiani Planum. Curiosity turned Gale Crater into a layered book of habitability. Perseverance turned Jezero Crater into a sample archive. This progression matters for the viewer because Mars is not a solved planet. It is a planet being slowly assembled in human understanding. Every generation receives a different Mars from the previous one, and the current Mars, organic-rich, water-shaped, geologically complex, potentially sample-returnable, and still unexplored at depth, is the most interesting version yet. Throughout the history of Mars exploration, no chapter has been more impactful than the era of rovers, robotic geologists that have driven across the Martian surface, examined rocks up close, drilled into the ground, sampled the soil, listened to the wind, photographed the landscape in detail, and sent back a relentless stream of discovery. Sojourner, the first Mars rover, arrived in 1997 aboard the Mars Pathfinder lander, a small, skateboard-sized vehicle that operated for 83 Martian sols. Its mission was primarily a technology demonstration, proof that a rover could be deployed, driven, and operated on another planet's surface. But it also examined the chemistry of Martian rocks in its vicinity, finding compositions different from those expected and hinting at the geological diversity that later missions would explore more deeply. Spirit and Opportunity arrived in January 2004, twin rovers of similar design, each intended to operate for 90 days. Spirit's landing site in Gusev crater had been chosen because orbital images suggested a possible ancient lake environment, though Spirit found mostly volcanic rocks initially and had to drive to reach the Columbia Hills before finding convincing evidence of past water. Opportunity's landing site at Meridiani Planum yielded immediate results. The famous iron-rich spherules, layered sulfate rock outcrops, and chemical signatures of ancient aqueous environments were encountered almost immediately after landing. Opportunity went on to operate for nearly 15 years, driving more than 45 kilometers in total, examining ancient impact craters, rocky outcrops, and the textures and chemistries of Martian sedimentary rock in extraordinary detail. Spirit operated for 6 years before becoming immobile in soft soil in 2009, where it remained as a stationary platform for another year before contact was lost. The last signal from Spirit was received in March 2010, and after months of attempts to re-establish contact, NASA declared the mission complete. Spirit had operated for more than 25 times its planned mission duration. Curiosity, which landed in August 2012, was a quantum leap in rover capability, car-sized rather than golf cart-sized, nuclear-powered rather than solar-powered, equipped with instruments capable of directly analyzing the chemistry of rock samples drilled from the surface, detecting organic molecules, and characterizing the radiation environment. Curiosity's primary finding, that Gale crater once contained a habitable lake environment with the right chemistry to support microbial life, and that the lake may have existed for millions of years, was one of the most significant scientific conclusions in the history of Mars exploration. Curiosity is still operating in 2026, more than 13 years after landing. Having driven more than 30 kilometers and drilled dozens of rock samples over the course of one of the most scientifically productive surface missions ever sent to another world. Jezero crater deserves special attention because it is not just another landing site. From orbit, Jezero showed the shape planetary scientists hoped to find, the remains of an ancient river delta. On Earth, deltas are especially valuable geological archives. When a river enters a lake, it slows down and drops sediment in layers. Fine-grained mud can bury organic material quickly. Minerals can trap chemical signals. Layers can preserve a sequence of changing environments: river channel, shoreline, lake floor, flood deposit, drying episode, renewed flow. If life ever existed in that environment, a delta is one of the places where traces might be preserved. That is why Perseverance's work in Jezero is so important. The rover is not just driving through attractive terrain. It is sampling a former lake system chosen because it combines habitability and preservation potential. Some rocks record igneous history, useful for dating. Others record sedimentary processes, useful for environmental reconstruction. Others contain organics or mineral patterns that may one day become central to the life question. The sample tubes are valuable not only because they contain Martian rock, but because each tube has context: where the rock was found, what layer it came from, what minerals surrounded it, what textures were visible at the surface, and how it fits into the broader story of the crater. Context is everything in astrobiology. A molecule without context can mislead. A texture without context can be overinterpreted. A sample from a known layer in a known delta in a known crater, documented by cameras, spectrometers, and geological mapping before it was sealed, is vastly more powerful than a random Martian meteorite found on Earth. That is why the Jezero samples matter so much. They are not just rocks. They are chapters removed carefully from a planetary archive. Perseverance, landing in Jezero crater in February 2021, carries the most sophisticated science payload ever sent to Mars, including instruments designed specifically to detect biosignatures. It is also collecting the sample cache for the Mars Sample Return mission, carefully selected rock cores sealed in tubes, cached in locations on the Jezero floor and delta that have been mapped from orbit, waiting to be retrieved by a future mission and flown back to Earth. In its first few years of operation, Perseverance has confirmed the ancient lake and delta environment of Jezero, found organic molecules in delta sediments, and returned thousands of high-resolution images and hours of audio from the Martian surface. Perseverance also carried, as a small technology demonstration, a helicopter called Ingenuity, a tiny, solar-powered rotorcraft designed to prove that powered flight was possible in Mars's thin atmosphere. Ingenuity's first flight, on April 19, 2021, was the first powered, controlled flight of any aircraft on another planet. It lifted off the Martian surface, hovered briefly at 3 meters, translated sideways, and landed, a flight of 39 seconds that was, in terms of historical significance, comparable in spirit to the Wright brothers' first flight at Kitty Hawk in 1903. What had been planned as a 5-flight technology demonstration evolved into an operational scouting mission. Ingenuity completed 72 flights, covered roughly 17 kilometers, and flew for more than 2 hours total before rotor blade damage during its final landing ended flight operations in January 2024. Before human missions are discussed as heroic milestones, they have to be treated as survival problems. Mars is not a backup Earth waiting to be occupied. It is a low-pressure, low-temperature, high-radiation environment with toxic soil chemistry, limited accessible resources, and no biosphere to absorb mistakes. A human mission to Mars would be less like moving to a new continent and more like building a small temporary island of Earth inside an environment that is actively incompatible with human biology. Every liter of air, every watt of power, every kilogram of shielding, every kilogram of water, every repair part, every medical choice would matter. This does not make human Mars exploration impossible. It makes it serious. There is also a difference between making Mars habitable for a mission and making Mars habitable as a world. A short human expedition could survive by bringing a protected habitat, suits, power systems, stored supplies, and carefully planned life support. A longer outpost could use local ice and atmospheric carbon dioxide to produce water, oxygen, and fuel. These are difficult but conceptually realistic goals. Terraforming Mars, transforming the entire planet into a place where humans could walk outside without pressure suits, is a different idea entirely, and current science makes it look far beyond any practical capability. Mars does not appear to have enough easily accessible carbon dioxide to thicken its atmosphere to Earth-like pressure. Much of what remains is frozen in polar deposits, trapped in minerals, or already lost to space. Even if all accessible carbon dioxide were released, studies suggest the pressure increase would be far too small to create a warm, breathable world. Adding oxygen would require planetary-scale chemistry over enormous timescales. Building a magnetic shield or importing volatiles would require engineering on a scale far beyond anything humanity can currently do. This does not mean Mars cannot host humans. It means Mars would host humans inside built environments, at least for any foreseeable future. Habitats covered with regolith, lava tube shelters, pressurized rovers, greenhouses, laboratories, and perhaps eventually settlements that are more like Antarctic research stations or undersea habitats than open cities. The romance of Mars should not erase its hostility. In fact, The hostility is part of what makes the project meaningful. A human presence there would be an achievement not because Mars is ready for us, but because it is not. The meteorites from Mars add another strange layer to the story. We have pieces of Mars on Earth already. They arrived here naturally, blasted from the Martian surface by large impacts, launched into space, and eventually captured by Earth's gravity after journeys that could last thousands to millions of years. These Martian meteorites are identified by the gases trapped inside some of them, which match the composition of the Martian atmosphere measured by Viking. They provide direct samples of Martian rock long before any spacecraft sample return. Most Martian meteorites are igneous rocks, basaltic material that tells us about Mars's volcanic interior rather than its ancient lake beds. They are scientifically precious, but they are not ideal samples for the question of life. They lack the carefully documented geological context that a rover provides, and their surfaces have been exposed to terrestrial contamination after falling to Earth. Still, they have taught scientists a great deal about the age of Martian volcanism, the composition of the mantle, and the history of water-rock interactions. The most famous Martian meteorite is ALH 84001, found in Antarctica in 1984 and announced in 1996 as possibly containing evidence of ancient Martian life. The claim was extraordinary and controversial. Carbonate globules, magnetite crystals, organic molecules, and tiny structures interpreted by some as possible microfossils. Over time, the scientific consensus shifted away from a biological interpretation. Most of the features can be explained by non-biological processes, but the episode remains important because it showed how difficult the life question is. Even with a real Martian rock in Earth laboratories, the line between suggestive chemistry and convincing biology can be hard to draw. That lesson still shapes Mars science today. The goal is not to find one interesting feature and declare victory. The goal is to build a converging case: geological context, mineral environment, organic chemistry, isotopic patterns, textures, and the exclusion of plausible non-biological alternatives. Mars has taught scientists to be patient. The sound of Mars is another small but powerful reminder that it is a real environment. For most of the space age, Mars was silent to us. We had images, spectra, temperature readings, pressure readings, and chemical analyses, but not sound. Perseverance changed that with microphones that recorded the Martian wind, the crackle of laser shots from its SuperCam instrument, the movements of rover hardware, and the passage of a dust devil nearby. The sounds are thin and muted because the atmosphere is thin and mostly carbon dioxide. Sound travels differently there. Higher frequencies fade more quickly. Everything is quieter, more compressed, less full than it would be in Earth's dense air. This detail does not change the main science of Mars, but it changes the feeling of the planet. A place becomes more real when it can be heard. The wind is not an artistic effect. It is moving gas in a real atmosphere. The rover is not an animation. It is a machine working on a cold plain under a pale sky. The laser clicks are not science fiction decoration. They are data being produced one pulse at a time from Martian rock. These sensory details help hold the viewer's attention because they turn the abstract planet into a place. Mars has weather. Mars has sound. Mars has moving shadows, dust on camera lenses, tire tracks in regolith, frost on the ground, and rocks named by teams of people who spend years learning the personality of a landscape they may never touch. The science is rigorous, but the place is also vivid. Looking toward the human future at Mars, the conversation has shifted over the past 2 decades from theoretical possibility to active planning. Even if the timeline remains uncertain and the challenges remain formidable, the appeal of sending humans to Mars, rather than only robots, is both scientific and philosophical. Humans can do certain things that robots cannot: recognize unexpected features, and make complex decisions in real time, perform delicate sample collection in ways that preserve context and detail impossible to replicate with robotic arms, respond flexibly to geological situations that weren't anticipated in mission planning. A human geologist on Mars, in a single day of fieldwork, could accomplish what might take a rover months or years to achieve, assuming the human is protected from the environment. The argument for human exploration is not that robots are inadequate, they have done extraordinary science, but that humans plus robots could do even more. The challenges are equally extraordinary and worth dwelling on rather than passing over quickly, because they are real challenges that no amount of enthusiasm can wish away. The journey takes 6 to 9 months each way, during which the crew is exposed to cosmic radiation, galactic cosmic rays, and solar particle events, at levels that significantly exceed the total career radiation limits set for astronauts working in low Earth orbit. These limits exist because radiation exposure is a genuine cancer risk, and the dose accumulated on a round trip to Mars under the protection available with current or near-future technology would increase cancer risk in ways that mission planners and ethics boards take seriously. Developing better radiation shielding or finding ways to reduce transit time is one of the central engineering priorities for human Mars missions. The thin Martian atmosphere provides minimal protection from radiation on the surface, somewhat more than open space, but far less than Earth's atmosphere and magnetic field together provide. Future Mars inhabitants would need to spend significant time in shielded habitats or underground to manage their accumulated dose during a surface stay that could last 18 months or more, waiting for the planets to realign for the return journey. The round trip, including a Mars stay, would likely take 2 to 3 years total. During that time, the crew must carry all the consumables needed or produce them on Mars. Water can potentially be extracted from subsurface ice. Oxygen can potentially be produced from the carbon dioxide atmosphere, as Moxie demonstrated. Food presents a harder challenge. The mass required to feed a crew for 3 years is enormous, and growing food on Mars requires solving multiple problems simultaneously. Artificial lighting or Mars sunlight supplemented to sufficient intensity, soil chemistry modified to remove toxic perchlorates, pressurized growing environments, and protection from radiation that would damage plant DNA in unshielded conditions. Communication delays of up to 20 minutes each way mean Earth cannot provide real-time guidance or emergency support. During critical moments, a medical emergency, an equipment failure, a navigational decision, the crew would have to act entirely on their own, with Earth's support available only in a consultative capacity after a 40-minute round-trip delay. This demands a level of crew autonomy, medical training, and engineering self-sufficiency that exceeds anything required of previous human spaceflight missions. The psychological dimension presents its own serious challenges. 2 to 3 years of isolation, confinement to a small habitat, constant proximity to the same small group of colleagues, no possibility of return if something goes wrong, the profound distance from Earth. These conditions have no close precedent in human experience. Antarctic winter over missions and submarine deployments offer partial analogies, but neither involves the absolute isolation and irreversibility of a Mars mission. The crew selection, training, and psychological support systems for a Mars mission will need to be developed with the same rigor applied to the engineering systems. The first human explorers on Mars, if and when they arrive, will also become planetary scientists in a way no rover can be. A rover sees through cameras, spectrometers, drills, and programmed sequences. It can be brilliant, durable, and precise, but it cannot improvise with the full context of a trained field geologist standing in front of a layered outcrop. Human geology is fast because the brain is constantly comparing patterns. This layer is different. That pebble is out of place. This fracture cuts that vein. This mineral vein must be younger than the rock it crosses. This texture resembles a shoreline deposit. This sample should be taken before the light changes. On Earth, field scientists make hundreds of such judgments in a day. On Mars, with communication delay removed from the surface decision loop, human explorers could do a kind of geological work no remote mission has yet matched. But this advantage comes with contamination risk. Humans leak biology. They carry microbes, skin cells, breath, waste, tools, lubricants, plastics, and complex organic contamination. If the central scientific question is whether Mars ever had life, then sending humans too early to the most sensitive astrobiological sites could damage the very evidence we want to preserve. This is one reason robotic exploration remains so important. Before people walk near the most promising deposits, scientists need to understand which regions require special protection, which samples should be returned first, and how to separate Martian signals from terrestrial contamination. The future of Mars exploration is therefore not robots versus humans. It is sequence and partnership. Robots map, scout, sample, monitor, and enter places too dangerous or too delicate for people. Humans, eventually, may perform deeper field science, repair instruments, drill more ambitiously, and respond instantly to the unexpected. The best future is not one replacing the other, but both forms of exploration becoming stronger together. Despite all of this, multiple national space agencies and private companies have published detailed roadmaps for human Mars missions within the coming decades. NASA's Artemis program, returning humans to the Moon, is explicitly framed partly as a proving ground for technologies and operational concepts needed for Mars. SpaceX has articulated a detailed, if ambitious, vision for a self-sustaining human city on Mars using reusable heavy lift launch systems. The European Space Agency, China, and other programs have all begun serious planning activities. Whether the first human landing happens in the 2030s, the 2040s, or later depends on funding, political will, and technological development, all of which are inherently unpredictable. But the trajectory is clear. The robotic missions of the past half-century have been, among other things, a long preparation, mapping the terrain, understanding the environment, developing the technology, identifying the most scientifically valuable landing sites, testing the systems that future humans will use or extend. Every Mars mission, from Mariner 4 to Perseverance, has added a layer of understanding and capability that brings the human landing incrementally closer. Whatever the ultimate timeline, the first humans to set foot on Mars will experience something entirely unprecedented. Standing on another planet, looking out across a rust-red landscape under a pale, dusty sky, Phobos rising in the west, the distant rocks of a world that has been waiting, in its cold and patient way, for billions of years for anything alive to walk across it. That moment, whenever it arrives, will be one of the defining events in human history. Not because Mars will be easy to reach or comfortable to live on, but because the decision to go, and the sustained effort to make it possible, represents something significant about the nature of the curious, searching creature that evolved on this small blue world and has been looking outward ever since. Let's talk, before we close, about what Mars still hasn't told us, the questions that remain genuinely open even after this long and intensive history of investigation. The origin, and even the persistence, of Mars's methane is one of the most carefully watched, most intensely studied, and least resolved questions in current Mars science. Curiosity has reported low background methane and occasional spikes in Gale Crater. At the same time, the ExoMars Trace Gas Orbiter, designed specifically to search for trace gases from orbit, has repeatedly failed to detect methane at levels that should be easy to reconcile with some surface reports. This mismatch is now part of the mystery. Either methane on Mars is extremely local and short-lived, or some detection and destruction process is not yet understood, or some of the apparent signals require another explanation. On Earth, most atmospheric methane comes from biological sources, microorganisms producing it as a metabolic byproduct. But methane can also be produced by geological processes, water reacting with certain iron-bearing minerals, thermal alteration of ancient organic material, or release from trapped subsurface reservoirs. This is why methane is interesting but dangerous to oversell. If it exists on Mars in real bursts, it would imply an active process. It would not, by itself, imply life. The exact nature of the subsurface, whether liquid water exists at depth, whether there are active hydrothermal systems, whether the putative subglacial lake beneath the South Polar ice cap is real, remains a cluster of open questions of profound importance for the possibility of present-day life. InSight's seismic data revealed Mars is not geologically dead, with hundreds of detected Marsquakes pointing to ongoing internal activity. Some of these Marsquakes appear to originate from specific regions, possibly associated with tectonic stress or residual volcanic activity. If any volcanic activity, however minor, is occurring in the modern Martian subsurface, the possibility of hydrothermal environments where liquid water and chemical energy might support life becomes significantly more interesting. The question of how Mars's ancient climate was warm enough for liquid water also remains partially unresolved. The sun was significantly dimmer when early Mars was warm and wet, roughly 70 to 75% of its current luminosity, the same faint young sun problem that planetary scientists grapple with for early Earth. Models of Mars's ancient greenhouse effect, even with a much thicker atmosphere of carbon dioxide, have difficulty warming the planet enough to allow widespread liquid water given the dimmer sun. Additional greenhouse gases, methane, hydrogen, water vapor in larger quantities, or others, have been proposed to close this gap, and some models can produce warm enough conditions with the right assumptions. But a fully satisfying, broadly accepted model of early Martian climate remains an active area of research rather than a solved problem. These open questions represent the honest frontier of Mars science, places where careful investigation has been done, where current instruments have reached their limits, and where the next generation of missions will need to go. Mars has been studied more intensively than any world beyond Earth, and it keeps revealing new complexity with each investigation. That is, in itself, a kind of testament to how deep and how rich a world it is. As we come toward the end, the strongest way to leave Mars is not with fantasy, but with the planet as it really is. Mars is there now, cold, dusty, thin-aired, and ancient. Perseverance continues its work in Jezero crater, powered by its radioisotope system rather than by solar panels, examining rocks that were shaped by water billions of years ago. Curiosity continues its long climb through the layered history of Gale Crater, where mudstones and sandstones have preserved carbon chemistry from a time when Mars held habitable environments. Orbiters continue circling overhead, mapping minerals, weather, ice, radiation, and terrain. On the surface and from orbit, Mars is still being measured. The samples Perseverance has collected are sealed in tubes, waiting for a return campaign whose architecture and timeline have become more complicated than anyone hoped. That uncertainty matters, but it does not reduce the scientific value of the samples. They are still among the most carefully selected pieces of another planet ever collected, chosen from an ancient lake and delta system precisely because such rocks might preserve the chemical or mineral record of habitability, and perhaps one day, if Mars was inhabited, the traces of ancient life. Mars has a particular emotional force because it is neither unreachable nor easy. It is close enough that spacecraft can arrive in months, but far enough that every mission is an act of engineering risk. It is familiar enough to have sunsets, dust devils, clouds, seasons, and dry riverbeds, but alien enough that a human standing there without protection would die quickly from low pressure, cold, radiation, and unbreathable air. It is the world next door, but the door opens onto a planet that must be respected. The dream of Mars has changed many times. It was once a dream of canals and civilizations. Then it became a dream of first flybys and first photographs. Then a dream of rovers, lake beds, organics, helicopters, sample tubes, and eventual human missions. The imagined Mars disappeared, but the real Mars became more interesting than the imagined one ever was. Because the real Mars asks better questions. It asks how a planet can begin with water and lose it. It asks how long habitability must last for life to begin. It asks whether organic chemistry on a cold desert world is only chemistry, or whether it may sometimes preserve a deeper history. It asks whether a small rocky planet can remain alive inside after its surface has become quiet. It asks what kind of courage, patience, and caution would be required for human beings to travel there, work there, and return. And it reminds us of something about Earth. We live on a warm, protected planet with oceans, a thick atmosphere, a magnetic field, and a biosphere that has endured for billions of years. Mars shows what a neighboring rocky world can become when those protections fade. It is not only a destination. It is a comparison, a warning, a record, and a question. The red world is still turning. Phobos still races across its sky. Dust still lifts in the afternoon sunlight. Ice still waits beneath the surface. Ancient deltas still hold their layered stone. Somewhere in Jezero crater, a sealed tube contains a piece of a planet that may one day be opened in an Earth laboratory, under instruments sensitive enough to read stories no rover can read alone. And we leave Mars there, not as a dead world, and not as a promised second Earth, but as something more honest and more interesting. A planet that changed, a planet that remembers, and a planet whose silence has not yet finished speaking. Good night.